Our next speaker is Gabriel Elkaim, and he's going to be presenting batch misalignment calibration of multiple 3-axis sensors.
First thing, I want to thank the program committee for selecting a lowly experimentalist for this crowd. So a little different. Okay, so basically a little introduction and background. Many UAVs, small satellites, sensing platforms, mobile platforms use 3-axis sensors on board, typically accelerometers, gyros, and magnetometers, to figure out their attitude or pose in the robotics world. And the sensors themselves are imperfect, need calibration, and they're used as a primary aiding source. So you integrate the gyros, but the gyros have biases. That bias drifts in time, and you often have an attitude offset. So you need to put all those together. So attitude, the full rotation required to get between your inertial coordinate system and your body fixed coordinate system. We need to transform the measurements. Often some measurements are in the inertial frame, some measurements are in the body frame. Need to combine them together to figure out where we are. There's several parameterizations to keep track. Direction, cosine matrix, quaternion, Euler angles, Rodriguez, axis and angle, lots of them. Lots of work done in this area. It's a sort of old and well-studied field. So the basic idea, it's a nonlinear problem. You propagate it by integrating the gyros in one of the various parameterizations you use. And you have an attitude estimate. You use the, you can propagate it with the skew symmetric of your body fixed rotations. And that works great, but the errors build up. They build up for a lot of reasons, and you need something to correct it or you just drift off over time. So requiring external aiding sources, just to correct everything. There's lots of different filtering methods once you have that external aiding source to bring it in. Again, I have a couple of my own, but everyone has their favorite that they use. And the one we're going to use is, for the aiding source, we're going to use these two non-collinear body fixed measurements that we know in the inertial frame and are measured in the body frame. Okay, so this is often referred to as Wahba's problem, after Grace Wahba, who proposed it as a little problem in Siam Journal in 1965. There are myriad solutions to this problem. Again, I have a couple that I've written. Everyone's got their own favorite. That works, but it assumes that you have, so these two measurements, you know them in the body, you know what they're supposed to be in the inertial frame, and you can do it. And you can see that with one, you can rotate it in, but there's an ambiguity about the axis of the vector that you can never resolve. And so you need two, and they have to be non-collinear. And one of the things is, for this to work, it assumes that the sensors have the same coordinate frame, which they might not, and that's the problem I'm addressing here. And that you've well calibrated the sensors, you've gotten rid of the null shifts, you've gotten rid of scale factor errors, you've gotten rid of any cross-coupling in the axes, all the sort of messy stuff where you say, oh, if I have perfect measurements, how do I do it? That's the easy part. The problem is, you don't. All right, so again, sort of just looking at it graphically, I have a known vector unit. We'll just do a unit vector to make it easy. A known vector in the orange inertial frame. I measure it in the body frame, and it's pointing out, and I have to rotate the body around to line up those two vectors. And of course, if I have just one, I have an ambiguity about where I am, because I can rotate about that vector and not get any better solution. So you need two, and the definition is they have to be non-collinear, right? You have to have some angle between them, or else it won't work. Okay, the solution I'm going to use in this problem, because I'm going to wind up solving Wahba's problem a lot in this solution, is I'm going to use Markley's solution, which is just a singular value decomposition. Two really nice things that come out of Markley's singular value decomposition solution is, one, that it will work even when this beta that you put together, the measurement, drops rank deficient. It will still give you an answer that has the minimal cost. There are multiple answers with that minimal cost, but it will pick one of them for you, which is nice. The other thing is, if you go through Markley's paper, it actually has a covariance that it will give you about each of the elements of the direction cosine matrix, which is what we're working in here. And the other thing, as I said, I mentioned that the sensors have to be calibrated in the first place. Other work I've done, and other people have done as well, on calibrating the sensors by simply tumbling the object. So if you have a UAV, you can grab it and sort of spin it around. If you have a small satellite, same thing. And the idea is that you can, using only the knowledge of what the magnitude of the vector should be, you can reconstruct the norm and kind of essentially spherify the data. And other papers that are referenced that you can look up that. All right, So to the actual problem at hand. So this is the misalignment problem. And the idea is that I have these two vectors that I'm measuring in the body frame. I'm going to pick one of them and call it the master and say, this one is correct. And I'm going to pick the other one, call it the slave, and say it is incorrect, in that it does not share a common axis with the master, right? Which we rely on to solve the problem. We said there's a misalignment between them. And the one key insight is that because these two vectors are known in the inertial frame, the solid angle between the two has to be constant. So as I take paired measurements and rotate through various attitudes, I'm going to get the error in that angle is going to project onto the different axes, and eventually I should have an observable matrix that I can back out. I can back out the misalignment from the slave to the master and say this misalignment matrix will realign the measurements of the slave into the master coordinate, and now I'm back to where I was before, and I can solve for the attitude. And all right, so that's it. And so the minimum observability is I need 3 paired measurements, right? And they have to be sufficiently geometrically diverse. More is better, especially if you have noise on the measurements, which if you're using real sensors, you will. All right, so here is the theory, all right, which is I'm just going to take this body and I'm going to rotate it into a whole bunch of different attitudes, and I don't know what the rotation is, unknown, right? But I do know that the angle between the two should remain constant. And so what I'm going to do is I have, so let's see over. So what I have is my body measurements are ideally this unknown rotation matrix multiplied by the inertial vectors, added with some, usually we use zero mean Gaussian noise on top of it. And then I have this fact that there's a misalignment between what the slave should be and what it actually measures. I have this misalignment matrix that this is the thing I'm going to try to estimate. And so that corrupts all of my secondary slave measurements are all off. But the key is that that misalignment matrix is constant in the body frame. It's fixed, right? In the body frame, not in the inertial. And so I have to keep track of where I'm going. And so what I'm going to do is I'm going to aggregate my measurements in the body frame into a large matrix, and then I'm going to take my estimate of the misalignment vector and I'm going to rotate all of the slave measurements by that misalignment. All right, so I have an estimate. I start with a guess. The guess is the identity matrix because it's a decent one to go with. I rotate everyone in, and so what we're going to use is we use these pairs. So we go pair by pair and solve for the rotation for every single observation I have. Then we take that rotation, we rotate the slave, the ideal slave measurement into where we think the attitude is, and we take that and the actual measurement and resolve for the misalignment matrix, and then reiterate until it converges. So it's a block coordinate approach. And so what we're doing is we're alternately optimizing for the individual rotations at every step with our estimate of the misalignment held constant. So that basically is n independent Wahba's problems, each which has its own optimal solution. Then we calculate the estimate of our misalignment, holding all the individual rotations fixed as known. And that's a simple Procrustes problem. And so we come up with this sort of joint cost function for both of them together. It's everywhere differentiable. Each subproblem can be optimally solved. And so this is essentially a block coordinate descent. And it always converges to a local minima. And the nice thing is because of the Markley solution, it works with heterogeneous or homogeneous sensors. In other words, it doesn't matter whether I have multiple of the same sensors or different sensors that are measuring in different ways. All right, and so we have an algorithm basically of how we do it. And there's a question of sort of what is your stopping criteria? How do you know you've sort of gotten to a point where you can't go any farther? So I've got 2 matrices that I'm trying to take the difference of. And usually what I pick the Frobenius norm. There are others. There's a good argument to be made that you can do different one. You can do the dot product between the axis of the 2 axis and angle representations of it as another sort of decent way of doing it, and take the difference between one and that. There's a number of different ones. They wind up being almost identical. But the idea here is that I just keep resolving, and then if I'm not converged, go back up and keep doing it. All right, so first step in all of this is to do some simulation work. All right, so we start, and this is with 4, so this is a little complicated. So let me go through the colors. So the black vectors are the original, those are the master measurements. The green dashed ones are the slaves that have been misaligned. All right? And the blue is where the slave should be with the misalignment matrix done. And the cyan arrow there, that is the axis and angle of the misalignment. That is the axis of the axis and angle representation of the misalignment matrix, and you can see it walk itself in. And so what you see is as the algorithm goes, it kind of walks everyone in. This is in a noise-free case. It converges to the Frobenius norm 10 to the minus 15 after 208 iterations. Right? And you can do the same thing with 12 measurements, rather, where it starts getting bigger, and all you can see is it looks complicated, but again, it walks itself in quite nicely. And then we can add noise. Now this is adding Gaussian white noise to every single body fixed measurements, both the master and the slave. So every component of it is done. And then here we get a convergence to within 10 to the minus 2 of the representation. And it's within the noise covariance of the Markley solution. So we're getting as good as we can given that we have corrupted noise in there. And then here's sort of just some cumulative distribution functions. It gets better as you get more measurements. Obviously, the problem becomes overdetermined. And so what happens is as soon as you get up there, you get within 98, 99% convergence rate, what you can do. And again, either the Frobenius norm or the transpose of the axis works better. When I did n equals 20, I added a lot of noise. One of the things that, because we're getting stuck in a local minimum, so essentially you reset your initial estimate to something else and see if it walks into the same place, gives you some confidence on what you can do. And if you constrict the misalignment to be relatively small, i.e. less than 6 or 7 degrees off on any axis, you get 100% convergence. Always gets it. All right. And then, of course, the fun part is to actually do this. So I had some experimental data. This was a small sat. They were testing the magnetometers in a Helmholtz coil. And basically completely misaligned, post-calibration aligned, and you can see sort of the norm drops. Also did it with UAV. With the UAV, this is sort of original tumble test. We had a 23,000 points on this one, so the algorithm took a while, but again, 241 iterations. It converges. No matter where I started, it always converges to the same one, so fairly confident. That's about a 4 or 5 degree offset between the magnetometers and the accelerometers. And so we have those, and then our dirty laundry. So here it is. Is there a better way to formulate the problem? Undoubtedly there is. Is there a better stopping criteria for the optimization? I'm sure there is, and I just haven't thought of it yet. Are they computationally more efficient? This isn't a particularly efficient way to do it, and it's doing it as a batch. Is there sort of a recursive way to do it? Possibly. Certainly should be able to improve the observability as opposed to just sort of hand wave it. Convergence is, can I... In Monte Carlo simulations, it always converges to the right one. It barely gets stuck, but I have to prove it, and I'm sort of stuck as to how. If the problem can be recast as convex, I don't think it can, but it might be, or parts of it might be. And the question is, can this be put into a recursive form so that it's an online estimation that keeps going as opposed to sort of one batch with all of your data? And with that, questions? Yeah. Only if you have a rate table, right? So if you have a rate table, then yes, you can, because you can put the thing on the rate table and have gravity and your rate. But without a rate table, it's very hard because unless they're sensitive enough to measure Earth rate, in which case you have something, mine aren't, yours aren't either. So short answer is I'd love to as well, but I need a rate table that spins at a constant rate so I can then impose a vector on the gyros, which is always the problem. Sorry, okay. So the gyroscopes measure angular rate, all right? The accelerometers and magnetometers are easy. The magnetometer measures the Earth's magnetic field. The accelerometer, if you're not accelerating, measures gravity. So these are two easy vectors that I have and I know where they are. The problem I have is the gyroscopes, because they measure angular rate, I need to impose a constant angular rate on the system that I can then move around. And so what we do, there's an instrument called a rate table, which is essentially a very, very high-end turntable that will spin at a very constant rate to give you that exact thing, and a one-axis rate table is 100K, roughly speaking. Get a three-axis one, and they go up from there, right? And so that's not something anyone has around, and then you would have to put your thing in a jig on top of the rate table and sort of keep moving it to different attitudes, and then spin it back up again, take those measurements, and then it would work. But I'm not sure if I have that kind of cache, I probably have better sensors. So it's
Next figure, start setting up.
I was just curious if the algorithm is sensitive to the choice of master, and is there any that
What happened to
the algorithm has not is actually completely insensitive to whether which one you choose as master slave.
There was an HTML extension. Oh, there's. Sorry.
And if you can ping pong it as a way to see that you get the symmetric, because one should be transposed the other, right? And so that's another cross check to see if you got the right one. You will get a consistent answer. Whether or not it is the right one remains to be determined.
All right, let's thank speaker again.